Okay, great. Well, here we are again, everybody. A new series of videos. This series of videos will be on Introductory Econometrics, Econ 316, Econometrics at the University of Wisconsin, Eau Claire. I'm Dr. Thomas Kemp, and hey, welcome to this series of lectures. Now, before I get into any of that stuff over there on the next slides, I want to make sure everybody understands that first of all, this is a course in Introductory Econometrics. Second, this is a series of video lectures to sort of facilitate student learning, right? So this is not designed as a whole substitute for a course in econometrics. You can watch it all through. You're going to learn a lot about econometrics, but you would learn more in a regular class. Second of all, again, this is an undergraduate level course, so I'm not going to assume or really use any advanced mathematics beyond simple statistics, rudimentary undergraduate statistics, and perhaps a little bit of algebra and calculus. And even if you've never taken calc, you should be fine with this course. And finally, then, this course is really designed, or this series of lectures, is really designed to work with the Studentman text. What is it called? Using Econometrics. Sorry, I have to look off to the side there. Using Econometrics. It's a great book. I recommend it. It's very easy to read and very widely available. So again, A.H. Studentman, Using Econometrics. Okay, so this is lecture 1, right? So we're just getting started, right? What are we going to do here in this first lecture? Well, in all these, I'll have, the items right at the beginning, what we're going to learn. So if you don't want to learn those things, you can go ahead. But you need to understand that I'm often going to build upon ideas from earlier lectures, right? So if you're more advanced, right, or you're working through a different course or something like that, okay, well, I want to learn about my multicollinearity or something. Okay, well, you can go to that video. All right. Anyway, so in this video, we're going to learn the super basics. What is econometrics? What do we use it for? What good is it? Why do I care about it? We're going to learn what is regression analysis. That is the dominant tool that we use in econometrics, okay, statistical technique. We're going to learn about the estimated regression equation, right? So we're going to learn some of the sort of fundamentals about how regression kind of works statistically. And then finally in here, we'll just do a simple, quick example of regression analysis. Let's define this idea, econometrics. What is it, right? Is it just like economics with a metrics on the end? Well, yeah, sort of, right? It's sort of that. Econometrics is defined as the measurement and analysis of actual economic phenomena. Across the social sciences and in some of the hard sciences as well, regression analysis has its applications. What is the correlation of local school quality to home prices, right? This is actually, there's a huge literature on this. And it's significant, right? So better schools means higher home prices, as you would expect, right? But economists, we have a pretty good idea exactly how much it impacts home prices. Myself, I've published work on, and have done obviously a ton of research on like how lake water quality impacts home prices. Because I'm speaking to you here from Wisconsin, right? And we have a lot of lakes, and so that question is really important for a lot of people to understand. Well, if we clean up the lake a little bit, does it boost our home values? And the answer is yes, absolutely. And we can prove it. Okay, so other questions, like do minimum wages lead to increased unemployment? Like you learn this in like Econ 103, right? Like minimum wage enters unemployment, but when you look at the data, does that actually happen, right? Because of course in Econ 103 it's ceteris paribus, all things be equal. Well, when all things aren't equal anymore, what happens? Regression analysis, as it says over here, right? Statistical technique that attempts to explain movements in one variable, or the dependent variable, as a function of movement in a set of other variables called the independent variables through the quantification of one or more equations, right? We're going to stick with one, right? Okay, and that definition is from the text that goes with this series of lectures, which you see over here, right? So what we're doing is we're saying, okay, we've got a thing that we want to explain, like could be something like sales, like annual sales of a product, right? And then sometimes it's stronger and sometimes it's weaker, right? Sometimes sales are stronger and sometimes sales are weaker. So that variable is moving around, sales. And we want to figure out, what's causing it to move. and we're going to come up with some ideas about what we think is causing it to move. And we're going to see how movements in those variables impact the variable that we're concerned about, sales. So for example, like we might think like, well, if more people live around our store, we sell more things. Okay, great. We may think like, oh, if it's sunny outside, we sell more things. Okay, great. If we advertise more, we sell more things, and so on, right? What regression analysis is going to allow us to do is actually to put some numbers to that. Right. Don't get scared here, right? First equation on the top there. You got a bunch of Greek letters, right? Greek letters. I can remember being a new undergraduate myself and seeing Greek letters in math class stuff suddenly a lot and being really worried, right? But don't, right? Don't. It's okay. It's going to be okay. It's going to be okay, really. Okay. So what we're saying here is how do changes in the value of x1 and x2, so that's in that equation, right, affect the value of q, right? Okay, this is our hypothesis, right? We're gonna hypothesize that, given the plus signs in front there, we're going to hypothesize that positive changes in variables x1 and x2 have positive changes on q. Q is a dependent variable. The x's are independent variables. Okay, so we're going to talk a lot more about this in a couple lectures from now when we talk about the assumptions of regression analysis. But x1 and x2 we're assuming are independent variables, and that their values, so the values of x1 and x2, are determined by forces outside of this model. That is, we're assuming that changes in q aren't causing changes in x. Okay? We're also assuming that changes in x1 don't cause changes in x2. Or reverse, that x2 causes changes in x1. Okay. Now you might say, well, that seems unreal. Okay, yes, that's right. That's a pretty strong assumption, and we're going to spend a lot of time later in this term talking exactly about how we deal with those types of problems. Okay, so what did I leave out, right? I didn't talk about that beta, that scary Greek letter, right? Okay, well, the beta terms, whether it be the first one or the second one, or the 0, 1 too, 0, 1, 0, 1's a little different. I'll come back in a second, but tells us what changes in q are produced by changes in x. In other words, it tells us how sensitive q is to changes in x. Okay, so for example, if we say that beta 1 is 0.5 in that equation from the last slide, this implies that every time x changes by 2, right, q will change by 1. Okay, so you can imagine this like, maybe if we're talking about like selling lemonade on the street corner, every time the degrees of temperature goes up by 2 degrees, we sell 1 more cup of lemonade in a day. Okay, right? So the beta term is an estimation of how that independent variable, in this case the weather, temperature, affects q, lemonade sales. Okay? Now, what regression analysis does is estimates those betas. Right? So what we're doing with all this is we're estimating what is the nature of that relationship between temperature and lemonade sales. I think most of us would agree that probably when it gets warmer outside, we're going to sell more lemonade, all things being equal, or hot dogs, or maybe not hot dogs, soda, or maybe more beer at the ball game or whatever. Right? There's going to be a positive correlation there. What regression analysis is going to do is allow us to estimate the specific relationship between those two ideas. Now, because we're estimating things, right? This isn't truth. This isn't what we're doing here isn't creating truth with a capital T. Okay? We're estimating relationships. And as a consequence, we introduce this idea of a stochastic error term. Now, stochastic, I'm going to be brief here, so experts, please forgive me for a second. But stochastic is essentially a specific type of randomness. Okay, so we're going to assume that errors in our estimation are somewhat a specific type of random. Okay, so in other words, we're not going to obviously be able to estimate things perfectly, but we're going to assume certain things about the errors in our estimation. Right? And you might say, well, that doesn't sound very good to assume, assume your errors are sort of appropriate. Well, yeah, you're right, it's not. But that we'll get back to that later in the term about how we either make sure that's the case, or if it turns out we're wrong about that assumption, how we fix it. Right? Okay. So introducing that idea, right, we get our sort of hypothesized relationship starts to look something like this we see over there. So from that, so on the top there, from that idea, right, so we've got our hypothesized relationship between these variables and specific dependent variables. Remember, keep that lemonade example in your mind. So like you might think x2s, well, that's temperature, right? And then y is like lemonade glasses sold or something like that. And from that, then we collect a bunch of data. We collect a bunch of data about temperatures and lemonade sales and a couple other things, right? And we throw that all into our regression analysis, and it spits out this result there in the third line. Something like this. Let's again keep the beta 2 is, let's say temperature. Okay, so 3.24x. Okay, so what that implies, what our estimated value of beta 2 there tells us is that every time x is going up by 1, okay, y is going up by 3.24. So if this is temperature and lemonade sold, perhaps our data is telling us that every time temperature goes up by 1 degree, we sell another 3.24 glasses of lemonade. That perhaps is a reasonable result. I don't know, right? But that's what that's showing us. Okay, now something else to note here about our output, this third line. We've noticed a little like hat over the y, right? Okay. This is important to note because this is how we note that this is the estimated value of y. Estimated given our regression output. Okay, so we're going to note when things are estimate, you're going to see those little hats over them, right? You'll see a bunch of them there further down. Once we've done that, then we can, also rewrite the generalized equation, right? So the equation on the top, okay, we can rewrite as with all these little hats here, and you notice now it doesn't have that error term on the end. Why? Because the first line, we're saying this is what we think it is, right? But we recognize there's a random component to that. And then if we're talking about an estimated relationship, well, that includes, right? Includes that assumption that we have this randomized stochastic element to our regression output. It isn't truth, right? It's estimation, okay? When we're doing this regression work, right, we need to be careful that we're noting everything correctly, where we are, what are we doing here? Are we hypothesizing a relationship? Are we estimating a relationship? Or have we estimated a relationship? Is this the estimated relationship? So on and so forth. So we just want to familiarize ourselves with some of the nomenclature associated with regression analysis. Another important idea, right? So we had that error term before, right? We also have this idea of a residual, right? Now, the two ideas are related. The residual, right, which is the difference of the estimated value from the dependent variable from the actual value from the dependent variable, right? So you think like, geez, what is that, right? Okay, well, let's go back to our lemonade stand, right? Okay, so let's say we estimated temperature went up by 2 degrees, right? So we're going to estimate that we're going to sell about, what would be 3.24 times 2, right? So like, 6.5 more. Probably 6, and I'm going to sell half a glass of lemonade. Right? We're going to sell 6 more glasses of lemonade, right? Okay, right? So that's the estimated value of y, given the change in temperature, right? Okay, and it turns out we only sell 5 glasses. Okay, right? So there's a difference between that, 5 and 6, yeah? Okay, that's our residual, okay? Now, the lower the value of our residual, right, the better fit our estimated regression line is. In other words, in sort of normal people speak, right, the lower value of the residuals that we observe, the better a job we did of estimating. Okay, right? So now if you understand what all that stuff is, it makes a lot of sense. It's really not that complicated, right? Okay. So now the error term, so that's what the residual is, right? Now the error term is the difference between the observed value of y and the true regression equation, okay? So the error term is a theoretical concept, right? It's a theoretical concept. It's not something we observe, it's an assumption. Residuals are observed, okay? So you can think of that error term as an understanding that, we're going to probably get the exact number of lemonade glasses sold wrong, right? But we would hope, right, this is our assumptions about the error term, we would hope that sometimes we'll be a little high, sometimes we'll be a little low, and when we balance all those errors out, it's going to be about right, right? The residual, on the other hand, is the idea of, well, what specific errors did we actually make in our estimated value of y? Getting towards the end here already, start with the simple idea, okay, regression analysis. What is the estimated height of a person given their weight? So we're going to say our hypothesis is this, right? Our hypothesis is that we expect that the greater a person's weight, x, the should be the greater their height, y, okay? Note we have, there's an error term in here, right? We allow for variations, right? Obviously, height alone is not going to determine weight, okay? Or weight alone is not going to determine height. I mean, lots of people are like me, that is, they're more rotund. Okay, so you estimated my height, like I should be more, like 6 foot or whatever, right? Maybe, I don't know, right? So there's going to be other factors, right, that influence this for sure. So, okay, so let's say we collect a bunch of data about weights and heights, and we get these estimated beta 0 and beta 1. Okay, so beta 0 is the intercept term. Again, more on that later. And beta 1 is our relationship. Okay, so we can write this, the estimated value of y can be calculated in terms of x. Right? So, in other words, what this is telling us, right, is if we enter in a bunch of values of weights, right, so if we collect a bunch of data about weight, right, we should be able to forecast somebody's height, y. Okay. Now, let's think about this a bit, right? Sometimes they're going to be too high, too low. Yeah, of course, there's going to be a lot of errors. But if we collect a lot of data about heights and weights, we're likely to get more accurate at forecasting height from weight, particularly if we gather a bunch of data from a wide variety of individuals. Okay. But we're not going to be able to do it perfectly. And the reason why we're not going to be able to do it perfectly in this case is because there's a lot of other variables that are going to play into this. Probably somebody's wealth has a fair bit to do about this. The cultural background they're coming from has a fair bit to do from this. Maybe there's metabolic factors that play into this too. I don't know. I don't know anything about biology or anything like that, right? I'm not going to pretend either, right? But I imagine that there's factors at play there. Maybe people's attitudes about their health or their age plays into this too, right? There's going to be a lot of variables that are going to be missing from this. And so our estimated value of height from weight alone is likely to be pretty poor, okay? But we're going to find that it's a start, right? And this brings me to my final point in this lecture, right? Regression analysis and econometrics is a scientific process of refinement, of moving towards knowing from not knowing. This super simple regression isn't going to get us any meaningful results. But these simple regressions like this may set us on the path of refining our hypotheses and over time developing more accurate estimations from more appropriate sets of independent variables. All right, so that's what all this stuff does. I've shown you a little bit of the sort of nomenclature of regression analysis. Hopefully piqued your interest a little bit about it, right? And in future lectures, we're gonna delve much more heavily into this, right? I'm going to show you how to use this, show you how to use the software packages, right? Well, at least one, maybe two of them. And you should really have a good idea about how you could apply this in your own perhaps workplace or into other work that you're doing. Okay, thanks everybody for joining me on this first video lecture in this series on Introductory Econometrics. I think it's going to be a lot of fun. I'm pretty excited to do this series. Next time we're going to be talking about OLS, or ordinary least squares, and we're going to get our hands dirty a little bit with that. You're going to learn a little bit about how we, actually do econometrics and sort of what goes on under the hood of regression analysis, so to speak. Okay, looking forward to it. See you there. Bye.